So today we have Abhraneel Sarma from.
Where are my meeting notes? Okay.
Today we have Abhraneel Sarma from like the computer science department. So he works with Jessica Holman, who works on how do you visualize uncertainty and things like that. So I took a class with her, which is how I met Abhraneel. And Abhraneel, so what they do is how do you display data, how do you visualize uncertainty? So that involves a lot of statistics, and he's been working on this package called Multiverse Analysis that takes a data set and does the analysis that all different kinds of analysis in like a systematic way, which is very useful to people in applied math because they don't know how to do that and they spend a lot of brain power figuring that out over many months. So maybe this is a way that will help you streamline your data.
Right. Thanks, Chetan, for the intro. So yeah, like Chetan said, I'm a PhD student in computer science. And so what multiverse analysis, and I realize now that the title, I left a semicolon in there, or like a colon in there, but anyway. So what it's supposed to do is it's a meta-programming library. So it's not like a library in the traditional sense, but like you write code to the library, which then it gets processed and it rewrites your code. So it's a statistical framework which is put forward so that people can report statistics more transparently, because there has been a lot of like problems in psychology and like the social sciences with the replication crisis and people publishing studies which don't replicate. So for most of this talk, I'll take the perspective of how multiverse analysis is used in statistics, but I'll try my best to like connect it for applied math workflows, which I don't know very well, but I'm going based on what Jitin told me. So anyway, so what happens in the typical data analysis is that you have some data, you do some analysis, and you get some result. In statistics, in a typical statistical workflow, your result is significant or not statistically significant if you, depending on whether you get a p-value, which is completely random. But what actually happens is that in the analysis step, which it's not a direct like one-to-one process, it's not straightforward always, and there are different decisions that like a researcher makes at different steps of the analysis process. So to give an example, let's say that you have outliers in your data, so you have to decide whether you want to remove them. If you want to remove them, how do you want to remove them, etc. So like both of these choices seem defensible, or at the very least like are reasonable. But then this is just one example of choices. So you have more choices like data transformation. So do you want to transform the data or not? And regardless of your decision at the previous step, you might encounter these decisions. And then similarly, like there are more than one way of like, what statistical model you want to use to analyze the data. And given what you choose, your results might differ, as seen here. So following any of these analysis paths will lead to a different result. However, all of these analysis paths are perfectly defensible in one way or the other. So now consider that a researcher happens to make a set of choices which resulted in a p-value of 0.05. So then they can, decide that, okay, yeah, this is a statistically significant finding, let's publish this. And this kind of leads to the problem of publication bias. So this is parodied in a website in 538, where they asked like whether how the US economy is affected by whether Republicans or Democrats in power. And so depending on how you define the parameters and what variables you use, you can basically fudge the results however you want. So if a researcher intentionally manipulates variables, inputs, etc., to the analysis, then this is known as p-hacking. Although in the real world, p-hacking does exist, it's probably not at this scale. But if we fail to acknowledge this problem, we might see more research with outlandish claims. So one example is like this study. So basically, how much variability is there in the data analysis process, right? Like it's hard to know. And so what a group of researchers did is that they crowdsourced a data analysis project. So like they asked 29 different research teams to do a they gave them a data set and asked them this research question. And so when you have to answer this research question, you might be faced with certain decisions. So one would be like how you operationalize skin color, right? Like that's subjective and that's kind of tricky. The other thing is like more simpler decisions, like how do you control for variables like a player position. Like so in soccer, there are different player positions, but then you can classify them differently. Like you can have very broad grouping of like midfielders, goalkeepers, defenders, or you can have like more granular like central defenders or strikers and wide midfielders, whatnot. So each of these factors require a decision, and which must be planned before one conducts any analysis. And different researchers may make different decisions, and that's like all of these decisions are valid, right? Like it's hard to know which is at least they're defensible. So that's so when they actually got the results from each research team, they found like different different research teams came up with very different conclusions from the study or like from their analysis. So here, like 2/3 of the teams found a statistically significant result indicated by the green dots. So one conclusion is that like, we should probably worry about referee bias in soccer. The other key takeaway is that like depending on who does the analysis, you might end up with different results. So the set of all analysis, like this 29 analysis, carries more information than any single analysis. But then this type of multi-team analysis is very impractical to do in practice. But it is very likely that each of these teams considered more than one approach and then they settled on one single approach. So this is kind of what multiverse analysis is, where all possible paths, analysis paths are performed and reported. So here, each of these analysis paths have to be like equally defensible. And it gets away from like, reporting one single idiosyncratic analysis and helps eliminate the degrees of freedom that a researcher has. So basically, multiverse analysis is supposed to address flexibility and degrees of freedom in analysis. So it's not just like in terms of transparent statistical reporting, but also you can do other things like sensitivity analysis. So you can actually think like, okay, you are not sure which of these decisions makes most sense. And you can, if you do a multiverse analysis, you can see like, how sensitive it is for each of your particular decisions, how sensitive is your final result to it. So then in a way it comes back to transparency, because then you can say that, okay, there are different ways of performing this step and they might change my results significantly depending on where you go. Whereas like there's another step, say in your analysis, and different ways of doing it, different ways of parameterizing that decision does not really affect the final result. And also other ways that maybe you have competing theories about what the like competing theories and how you would model that theory. So you can use this to like test out all of those theories and look at the results and then say that this model probably best describes the phenomenon that's happening. But then the problem is that multiverse style analysis is difficult to implement. So the first paper which proposed it did something like this, which is multiple control nested for loops and like custom control flows using if-else statement. Probably a terrible idea because you can't like really replicate this and it's not reproducible, which is ironic. So we have, there are a few tools which have come out recently to support this. So there's the Multiverse R library, which we created, which lets you create, implement multiverse analysis in a principled manner. There's another tool that folks at University of Washington have created, which is called BOBA. So BOBA is language agnostic, domain specific language. And so if you are really interested in creating multiverse analysis and you refuse to learn R, then you can check it out because it supports Python. So I'll just give a quick demo about how the package works. So I'll focus on this.
I have one question.
Yeah.
So previously, when you showed the bad example, right, of multiverse analysis, the for loop, right?
Yes.
Why is it not reproducible? Everybody can write the for loop, right?
I mean, it is. So I guess more in terms of reproducibility, I guess like if you have the exact code and stuff, you might be able to replicate it. The problem is that debugging this is very challenging. There are other things which, I mean, also like, you have to, it's nested for loops, right? So you have to keep track of everything. And because you're multiplexing, so if number of like different analysis that you're considering rises exponentially. So this thing becomes really hairy. I mean, also like, I guess it's not super transparent because this code is hard to understand, even if you are familiar with R syntax, because it's so convoluted. So yeah, so then for today's case study, I'll focus on this study which claimed that female hurricanes are more deadlier than male hurricanes. There are many bad studies out there. So this slide shows like what a quick implementation of this original paper looks like in R. So first you load the data from a CSV file. Then what you do is you remove two data points for the two hurricanes which which had the most number of deaths. So which is their method of outlier removal. And then they create a new variable, Z pressure, which is basically like scaling the pressure variable inside the hurricane to a value between 0 and 1, I think. Doesn't matter. And then finally, what they do is they do a regression model where they estimate the number of deaths, and they use as predictors the masculinity or femininity of the name of the hurricane. And they have some other terms. Again, not that important. But yeah, so then one example of a decision that is kind of subjective here is the outliers. So they remove the two outliers, Katrina and Audrey, which are supposed to be the two most devastating hurricanes in terms of the number of deaths. But then, why are you excluding outliers? Like you can try to fit a model which is more robust, and you probably shouldn't remove outliers, or you can just remove one outlier. So that gives us, say, 3 decisions that we have. And so that code, which removes the outliers, transforms to something like this, where you have hurricane, then you're filtering. So filtering is like removing rows from a rectangular data frame. And so this is the part where we come into the multiverse package. So whenever you want to make some local modifications in your code, you use the branch function. So branch is like basically saying that you're forking into different paths right now. And yeah, so within the branch function, you'll specify alternatives. And the branch function takes in a couple of arguments. So one is the name of the first argument is the name of the decision. So you need to like give the decision a name so that you can keep track of it later. The subsequent arguments, and you can give like any number of them, they are they're of the form option name tilde option value. So the option name and tilde is optional, but it's good practice to have them so that when you're looking at like all the things that you've created, you have like a good nomenclature for things to keep track of. So yeah, so basically what this does then is that once you execute this R code, it'll create 3 versions of the same R code by capturing what you've written. And this results in 3 distinct analyses. So this is why I was saying like Multiverse is kind of a meta programming library, because it doesn't actually evaluate the code you've written directly, but it'll take it and it'll compile it into 3 different versions. So here we run into one problem, because we cannot, because whatever multiverse code that I showed you before is not like actually valid R syntax, because R will, I know why, but I mean, it doesn't allow the flexibility of like, trying to create different branches of it. So what we instead have to do is that we capture the code before it gets executed in R. And I'm assuming that's probably going to be same in any other programming language. And we, before it gets executed, we capture it and then we process the code. And to enable the processing, you need to add some syntactic sugar. So basically the first step is that you would load the multiverse library like any in any other language. And then we have this thing called a multiverse object. So the idea is that this object will contain all your subsequent analysis. And then depending on how you, depending on how you write your code, like are you writing it in a notebook or you're writing it in a script, like the next steps differ. So in R Markdown, so which is basically what Jupyter notebooks are for Python, R Markdown is for R. Code is written into code chunks. So if you want to write multiverse code, then you'll have to create a dedicated multiverse code chunk. So code chunks are created using this delimiter. And if you're creating a multiverse code chunk, so you just use this. You'll replace the previous one with this. And there are a few additional items that are additional arguments that are required. So like you need to pass in and inside. So the first argument is the name of a code chunk. So you might want to name it. If you are using a shortcut to create the code chunk, then it'll auto-generate a name. The second argument is the name of the multiverse object. So that one is required, otherwise it'll throw an error. Basically, then what we do is we take this code and then we evaluate it inside the multiverse object. Okay, so in our scripts, there's more syntactic sugar involved. So you first need to say that like, okay, we are writing this code inside the multiverse. So you use the inside function. The first argument is the multiverse object. And then whatever code you want to write, you put it inside curly parentheses. So what this does is it basically lets us capture the unevaluated expression. Yeah. And then finally, when you're done writing your code, you have to execute the multiverse. So what we do is we don't actually execute it as you're writing or even as you're running the code blocks, because let's say that like you have 200 different analysis paths. We want to optimize the execution for you. So we run only one analysis path, which is like the first combination of each decision that you made. And so if your code is like, going wrong because of things which are not related to the multiverse, then you would get some error. Otherwise, you can keep executing it. And when you run execute multiverse, you will get some errors if your code has bugs inside the multiverse code. Anyway, so give maybe a quick demo in R, because there are other things which are probably more relevant. So like, for instance, this kind of syntax is probably not super optimal if you want to like, multiplex over a continuous parameter. So like oftentimes if your input is like, okay, I want to see if I want to, take every value from 1 to 10 and see how that changes the output, and this kind of syntax is not optimal. So for that, let's start here. Did I not? Okay, so I think I forgot to set up the keyboard shortcuts. Why isn't it displaying. Ah, perfect. Right. So I can specify whatever version shortcut I want, because no. Oh, okay. So, I don't know why it's not working, but okay. So anyway, like I said, it'll, if you use the keyboard shortcuts should work, but also you can use an add-in, and you can create a code chunk like this, and it'll create a code chunk for you. So I think okay. So one way of like declaring a branch with continuous parameters would be something like this. So you use the options argument, and then you can say 1 to 25. So this is basically like a way of quickly declaring a list in R. So this generates like a list from 1 to 25. So if I do this, wait, oh, forgot to give it a name. Oh, sorry. And then, so you, I guess there are two things that happens here. Okay, should actually restart the session. So much crap there. So here, if you can see, what happens is that the value of X is 1. Like I said before, what the multiverse package will do is that it'll execute the first decision, the first choice in your decision space. So here, X is taking values from 1 to 25 in different universes. So the first universe is 1, so it takes the value of 1. But then you have, I mean, this is a very naive and simple multiverse, but basically you have a multiverse of 25 rows. And if you want to like look at what each multiverse contains, then you can, the code column in this table has the code that you've declared in each multiverse, in each universe of the multiverse. So universe is basically one analysis part. There are other things that I'd probably point to the reference. So for instance, you might have one decision in the multiverse, and based on that, a certain subsequent decision downstream might be incompatible. So then you need to define conditionals. And so one way of doing it is like, so there is a way of doing it, which might be too much to demonstrate right now, but you can, there are examples in the website for the package.
Give an example with like two folks. One is one, like 1 to 25.
Okay. I mean, I can give an example with the hurricane data set if that makes more sense. Okay. So again, going back to the hurricane data set, so this is just the data processing step. And then this is the analysis step that it did. So if you want, I want multiverse code block here. So I'm just doing the first step is like doing the filter operation that I showed in the slides, which removes like the 2 outliers based on number of deaths. This is kind of a weird way of writing it because I'm saying no exclusion. Wait. Okay. So basically, when I do no exclusion tilde true, it just says that all the rows in the data set are valid because it evaluates to true. So whatever expression it evaluates, if it evaluates false, then those get excluded, which is and this one removes one data set and remove the other one. All the parentheses lined up. Okay. So then this is one filter operation. So then I can also decide to exclude. Where's caps lock on? I can also decide to exclude like hurricanes based on the damage done. And that so by default, the first option is no exclusion. Just these things. Up. What are the hurricanes? So Sandy and Andrew are the hurricanes with the most. So then basically I run. Hold on. All options should be of the same type. This is of the same. Oh, parentheses. There's some. I'm missing parentheses there. So then basically this should create a multiverse of size 3, size 3 into 3, which is 9. So then, no. This is, oh, okay. Right, because I did it with the previous multiverse, which is combining. So now it's like 25 times 9, which is 225. Because I declared a parameter in the beginning. But then, yeah, so like basically this will result in an exponential increase in the number of analysis that you're considering, which is which can be helpful, also frightening. But yeah, so I guess questions.
We have options for like what kind of analysis you want to do.
What do you mean?
Like, we have this data set.
Right.
Now you want maybe do like a lead regression or some other kind of regression. Are there options for that?
So I mean, you can do it using like other R packages, right? So like instead of trying to offer a dedicated package like function in this library, what we allow the user to do is that they can use there's a linear regression function in R which does a pretty good job. So then we let them use that function. And so basically, even if you're not trying to like, you don't have to write a linear regression function for a multiverse analysis. You can just use your regular linear regression function here. So I have the data frame here, so then I can estimate that. Do it in a different code chunk. Last time because that. Right. So then basically this LM function is like a linear model function in R. So you don't have to like, you can use the existing programming like APIs in R to add to it. And the other reason is like, if you want to create your charts and stuff like that for each universe in your multiverse analysis, you can use like, because R has like a pretty decent set of packages for making graphs and charts. So you can add to it. And because what you're writing is R code, even if you're writing it within a multiverse, it'll just get executed multiple times. And everything will work just as fine. So which is kind of why it's like, yeah, meta programming.
This is showing the result for the very first.
Right. So then if I want to do so the step would be execute multiverse, and I do it for each of the 225 multiverses. The one tricky thing is how you get results from it. So to expand, then okay, so I stored the linear regression model in here. So then what it does is in that table, it'll create a column of that variable from each universe. So now I can just inspect the column depending on how what I care about. So like, let me just and this is like our syntax, but for the second universe, this is how I would extract the result, which is a bit complicated, but there are other methods for extracting results from each universe. But yeah.
those filtering steps that you showed before, and like those branching, that's on different ways that you would filter your data to begin with.
Yeah.
Is it the case that you would then apply like a linear model or some other model to every one of those, or could you just apply that to like a subset of those options?
You can, so right now it's applying the linear model to all of them, but there is a way to apply it to a subset. So for instance, over here, what I could have done is just gonna come up with stupid names for now. It's, I mean, in the absence of a better alternative, I'm just gonna add the variable 1 or maybe NA, the ones that I don't care about. And so the syntax is something like this: percent when percent. This is where the naming comes in handy, that outliers equals okay, this has become a bit of a complicated mess, but right, so I guess this should work where you only fit the linear model when you're not excluding any data in terms of that outliers. So the let's see if actually that's the case. Parameter names should be let's say the multiverse. Yeah, so in some cases, whereas I guess it's in the second universe itself, we are not fitting a linear model to it. So you're conditioning on your previous decision. So yeah, some of the syntax is kind of weird. We tried to map it to like, an if-else statement, which is, I guess, kind of what this is. The problem, I mean, we're trying to change this actually. So we actually want to implement the if-else syntax instead of using this weird percent when percent. There is a bug in the R code that doesn't let us do that. Cool. Yeah, thank you for the opportunity.